so sorry. Okay, so let's start. So hello and welcome everyone to the 14th lecture of our CUDA program. So in the previous lecture, we saw how to implement mutual exclusion for two threads. And for doing that, we saw multiple examples, and and we saw that there are issues with those examples, right? So few of the examples were not following the progress requirement, and few of the examples were leading to deadlock and so on. And towards the we saw those issues, and towards the end we left off with this slide, right? We saw this Peterson's lock, and if you remember, this Peterson's lock is the perfect way of implementing mutual exclusion for two threads, because it guarantees mutual exclusion for two threads. It doesn't lead to deadlock also, and it ensures progress. So all the three requirements are met by the Peterson's algorithm or the Peterson's lock, and hence it's the perfect way of implementing the mutual exclusion for two threads. And then at the end, we asked ourselves the questions that what about n threads? Let's say we have more than two threads, then how can we implement the mutual exclusion for n threads? So we'll be seeing this today. So first of all, before moving to the today's content, let us briefly outline what we are going to see today. So in the today's lecture, we'll be saying how to implement mutual exclusion for n threads using something called as bakery algorithm, and we'll see whether we can use that bakery algorithm on GPU or not. We'll understand that bakery algorithm in detail, and then we'll switch towards the next aspect of the synchronization, which is atomics. We'll see what are the atomics, and how they are different than this control and data flow. Then we'll see different kinds of atomic instructions, and also we'll see multiple scenarios or multiple use cases where we can apply the atomics. And then towards the end, if we get some time, then we'll start with the first atomic instruction, which is atomic guess. And yeah, probably with that we'll stop for the today's lecture. So with this, let's get started with the today's agenda. But before moving on, let me quickly see if there is anything in chat. Okay, there is nothing in chat. Fine. And recording is okay. Okay, so I think then let's start with the today's with our today's agenda. So let us start with this bakery algorithm, which I said that it's the algorithm for implementing the mutual exclusion among the n threads. And if you see this, the name itself suggests that it's something related to, this bakery is not the name of any person, but it's the bakery shop actually. So if you see, this name suggests something. So if you people know, then if you go to some food court or some bakery, then you might be given some token, and based on that token, based on the number on that token, you will be served by the shop owner or shopkeeper. So that token indicates when your turn will come for the service. So if the token number is larger, then probably you need to wait for longer time, and vice versa. So this is that is what is bakery algorithm. But here, instead of serving people, here we are interested in serving threads. And how do we want this? How do we want to serve the threads? We are essentially serving the threads, meaning we want each and every thread to execute its critical section, but they all can't be served simultaneously. That is, they can't execute that critical section simultaneously. So to resolve that, to ensure mutual exclusion, what we do is we follow some similar pattern that we use in this bakery, that is bakery or food court or some shop where that token number is given. So each thread is given some token number, we'll see, or some label, and based on that label, it will be allowed to enter the critical section based on that label, and that label denotes when it will enter into the critical section, and so on. So we'll see this thing in detail. So that's a brief overview about the bakery's algorithm. And this bakery's algorithm was devised by Leslie Lamport, and as I said earlier, it works for n threads, not just for two threads. It works for more than two threads, which is n threads. and it maintains something called as FCFS, that is first come first serve order. So threads which comes first will be served first, similar to how we have in the bakery, right? The uh, the customer who will be arriving first will be served first because their token number will be smaller than the customer will be who will be entering later. Yeah, so I hope you are getting that. So it maintains FCFS order in the similar way how we used to have it in actual bakery. And yeah, this yeah, for doing that they use this ever increasing number. The same in the same manner we have that token number in that token. So yeah, they use this ever increasing numbers. And yeah, with this, let's see the code for the bakery algorithm. So as we did in case of Peterson's algorithm, we had this flag, but just for two, it was just of size 2 because there we just had 2 threads. But here, since we are working with n threads, we now declare flag of size n. And this flag, which is the array of size n, is now initialized to all false. All elements are inside it are initialized as false. And apart from that, for maintaining that token or some number, we use something called as label. Label is again an array of size n. So the ith entry in this label array will denote what is the status. What is the token number of that thread. So let us say ith entry is some, let's say 100, then the token number of that ith thread, the thread having ID I is 100. So token number of that thread having ID I is 100. And initially all the token number is initialized to 0. And apart from that, yeah, then comes the main thing, that is lock and unlock methods. So each thread that wants to enter into the critical section will execute this lock function. Then they'll, if they succeed in executing that lock instruction, basically if they don't stuck here at this while loop, then they'll proceed to critical section. And then after finishing critical section, they'll execute this unlock method. So I hope you're getting this to lock and unlock methods. Okay, so now let us go and see what is there inside this lock and unlock method. First, let us look at the lock method. So first of all, we are getting the thread ID. So each thread will store its thread ID in some variable called as me. Then, as we do in the Peterson's algorithm, we indicate the readiness of the particular thread. So let's say thread I wants to enter into the critical section, then it will set flag of I equals to true. That is flag of me equals to true. This indicates that this flag is willing to enter into the critical section. So by execution of this statement, thread is in some sense expressing its willingness to enter into the critical section. And yeah, after that, what each thread does is it actually generate its token number or label. So how does it, how it does it is like it go I mean it it picks label as the maximum out of all the currently assigned labels. So please note that this all the currently assigned labels are here declared as array of size n. So out of all, maximum value out of all the currently assigned label plus 1. So that will be the greatest value. So okay, so let's say the thread, okay, so maximum value in this label array was, let's say 10, which was assigned to some of the thread. And let's say some thread, let's say 15 came and it want to know what is my label. So what it will do is it will go through all the currently assigned labels, and the maximum of those is 10, and 10 plus 1 is 11. So the thread 15 will get 11 as its label. So I hope that is clear. And after doing that, after setting flag as true and setting the label as 1 plus 1 plus max of all the labels for the all the threads, what the thread does is it checks if there is any other thread whose ID is not equals to my ID. So k not equals to me. If there exists k not equals to me, meaning if there exists some thread whose ID is not equals to my ID, me is the ID of that thread, and if that thread has expressed its willingness, right? Setting flag is expressing its willingness to enter. So if that thread has expressed its willingness to enter the critical section. If that is true, and if the label of that thread is less than the label of mine, I mean, if it has the lesser value of the token number than the value of the token number that I have, then in that case I have to wait, because I need to I need to give that thread the chance because it has lesser token number. So I'll be waiting in this while loop. And yeah, please note that this is lexicographic comparison. So it's not just based on the label, but it's also based on the ID. So okay, let me. Okay, so let's say, let us assume this scenario. Uh, let's say both of the threads have same label. Then in that case, let's say both of the thread got the label as 1, but one of the thread has ID 0 and one of the another thread had the ID 1. Then in that case, thread with ID 0 will get first chance, because after, if you, I am hoping that you are getting it. This is the lexicographic comparison, and 1 comma 0 is less than 1 comma 1, because after comparing the label we compare the IDs. So if label matches, we'll see who has the lesser ID, and if the labels are itself not matching. So let us take this example. 2 comma 100 is less than 3 comma 10. So please note that first of all we'll be comparing the labels. So here the label itself is lesser, I mean lesser than the label of this thread. So in this case, this thread will get first chance, even though it has higher thread ID, but its label is less. So first of all label is compared and then the ID. So I hope you are getting this, that this is the lexicographic comparison, in which we are comparing label and we are using label and ID as a tuple to compare who will get the first chance. So this based on the label and the thread ID, and based on the willingness of the threads, will be making sure that only one thread enters into the critical section. So yeah, I hope that you are getting this. So yeah, based on whosoever satisfies this condition, that thread will be looping here, and other thread for whom this condition is false, it will enter into the critical section, and after entering the critical section it will execute this unlock method. So what this unlock method does is it sets flag of TID equals to false. And what does this mean? Setting flag of TID equals to false. That thread is saying that I am no longer willing to enter the critical section, since I have already finished executing my critical section. So that is what is lock and unlock method. Any questions up till this point for on this slide? Any questions? Okay, there is some question. Sir, explain the loop again. Okay. Yeah, let us look this loop again. Okay, so let us understand this loop again. So what this loop is saying is, first of all, first of all, we need to understand two things, right? Whenever thread wants to enter into the critical section, it will set, it will set its flag, which is saying that I want to enter the critical section. It is expressing its willingness, and then it is calculating its label. Now let us come to this while loop. What this while loop is doing is, it is checking if there is some thread apart from me. If there exists k that is not equals to me, there is some thread which doesn't have my thread ID and it is willing to enter into the critical section. And if its label is less than my label, if it has label less than my label, then I'll wait for that thread to finish the critical section, and then only I'll enter. Is what is this while loop checking. And if both have the same label, they'll go by, it might happen that both have same label, right? Then in that case ties will be broken by this thread ID, which is k and me. Please note that k and me both have the thread IDs. K is the thread ID of some another thread, and me is the thread ID of this current thread. So I hope that this is clear Yeah, I hope that this is clear, Gokul. If there are any questions, then you can ask for me.
Sir, me colon flag K, what does it imply? Please explain again.
Okay. This one, right? Okay, so okay, I mean this
Yes.
is not a exact C syntax, so please pardon me for that. But such things are not present in C, right? So there exist and all those things are not in C. So it's some kind of a pseudo code. So please uh, ignore that thing. But let us understand this. I mean, don't think that this is a C syntax. But what this essentially tries to do is that it checks if I mean, this me colon flag k is something like it goes through all the thread IDs. Sorry, it goes through all the flags, and if it checks if the there is some flag set to true. I mean, essentially, it is going through all these flags. I mean, it's kind of a for loop which is going through all these flags, and it is checking if any of the flag value is true, and if it is true, it should not be the it should not be at the index which is my index, which is the thread ID. That is how this thing this small this entire thing will be implemented in C. But this is some kind of a pseudocode, so please ignore that. This I mean, this try to understand what it is trying to say rather than thinking it from a very syntactic or C style of writing it. So I hope you are getting this thing that I was trying to explain. If any further clarification is needed, then please let me know. Sir, it's logical and in the while loop, right? Yeah, it's a logical and. It's not a bitwise and, it's a logical and. Yeah. Sir, how will the k value be determined? So again, k value is, I mean, what each thread is doing. It is going through all the value. I mean, all the elements in that flag array, and that index inside that flag array determines the k value, right? And k value is nothing but the IDs of all other threads apart from the thread, I mean current thread. So I hope that is clear. Okay, this is good that people are understanding and asking the questions. So yeah, well, this is good. So let's move on further. So I have three questions for you. Yeah, I have exactly three questions for you people. First question is, let us say that let me come back here only. Okay. Shit. Okay. Anyways, let us. I have three questions for you people. Let us say I replace this this part of the condition. There are two parts, right? This is the first part, and this is the second part of this while condition inside the while loop. So let us say I replace the second part by this uh, label of label of k less than label of me. I just replace this entire thing. I just replace this and not entire thing, but this part uh, with this thing. Then what will be the output of the code? This is the first question. I mean, output in the sense whether it will guarantee mutual exclusion and progress and all those things. First of all, will it guarantee the mutual exclusion is the question. So again, I repeat the question. I replace this part, the second part of the condition after this logical end by this thing. Then will it guarantee the mutual exclusion is the question. Okay, if you are telling there might not be a mutual exclusion, then why? because label values max might change while calculating. Okay, it might change while executing, but can you give some execution pattern which might cause mutual exclusion to violate from this slide? You can either unmute yourself or can type in chat. Sorry. Okay, there can be two equal label values. Okay, there can be two equal label values, but how is that possible? Is that I want to know from you people. How can there be two equal label values? Can anyone put some comments about that? So we are just trying to brainstorm. So like we want to understand if changing few bits can uh, do some sort of issues with this code or not. So can there be two, is there a way in which we can get same label values for different threads? Is it possible for this lock method? Okay. Okay, I guess there are no responses. Okay, in that case, let us try to understand. Okay, so my question was this, right? That I want to replace, I want to replace this entire thing with just that small thing in which there is no k and no me. So we are just comparing the labels and not the thread IDs. So in that case, as I explained, or as someone was pointing out, not as I explained, but as someone was pointing out, if we are just comparing based on the labels, then it might happen that two threads might have same label, and if that happens, then I mean, both of them will enter into the critical section because label of k is less than label of me will be false for both of them because this is, please note that this is strictly less than. So that will be false for both of the threads and both of the threads will enter into the critical section. But the question is, when will it happen that both the threads will get the same value of label? Well, it can happen. Yes, it can happen in this case, and it will happen here. See, when you, let's say, both of the threads executed this instruction, this entire instruction simultaneously, and both of them try to find the value of max inside this label array simultaneously. And let us say both of them found that okay, max value is 0. In that case, what they will do is they will do 0 plus 1, which is 1, and will tell that okay, my label is 1. So for both the threads, the label is 1. And assuming that we haven't kept this k and me here, in that case, what will happen? Both are willing to enter into the critical section. So flag of both is true. So both are winning, and for both of them, label of k is less than label of me is sorry. Both of them are winning into the critical section. So this flag of k is true. Okay. So again, so let us say both of the threads wants to enter the critical section at the same time, and let's say this k and me is not there. We just have this label of k less than label of me as the condition, along with this condition, and they both set flag equals to true, flag of me equals to true. They set label equals to 1 plus max label, and both of them simultaneously found the max value out of this label array, and this max value found was 0, and 1 plus 0 they both did they both found max value inside the label array as 0. So 1 plus 0 will be 1, and both will get label of me as 1. So for both of them, label will be 1. And now when they try to enter, they execute this while loop, flag of k will be true because they will find some another thread which is willing to enter into the critical section. But this condition will be false for both of them because label of k is less than label of me will be false because 1 is less than 1 is false for both the threads. So both of them will enter into the critical section. And so in that case, mutual exclusion is not guaranteed if we remove this k and me from here. So point that I was trying to highlight here is that this kind of thing is kind of inevitable for this bakery's algorithm. We need to have tiebreaker here, otherwise it might happen if we just keep this thing, if we just keep this thing, then it might happen that we might end up losing mutual exclusion. So it might end up that both, I mean, it might happen that both of the thread entered the critical section. I hope that is clear. So that was the first question. Second question is simple. Let us say that again I want to replace this second part of the condition after this logical end with this thing. K less than, just this simple thing I want to use instead of that label of k comma k less than label of me comma me. I want to replace it with just this simple thing. If I do that, then what will happen? Is mutual exclusion guaranteed? Is progress guaranteed? Or can there be a deadlock? I want you people to think about it. If I replace this by this simple condition, then what will happen? Please think about it and post your answers to the chat. So Varun is saying progress is not guaranteed. How progress is not guaranteed? Well, this is correct observation, but I want you to elaborate how progress is not guaranteed.
Yeah, so essentially,
Hmm.
can you hear
Yeah,
me?
go ahead. Yeah, I can hear you. Yes, go ahead.
So let's say the first thread comes and the thread one reaches this particular point first, and then thread zero is still waiting on some thing, doing something beforehand. In that case, it finds that k less than me is not true for um, the thread one.
Okay.
Oh no, so it's actually uh, yeah, that actually seems right. So yeah, k less than me um is actually true, and it waits for that particular point. Uh, yeah, that's
Okay, okay, so I'll probably elaborate more upon it. So, yeah, your observation is correct that progress is not guaranteed, and that thing is also correct that thread with greater thread ID will keep on waiting here. But let us try to see it in a different way when it might happen that it might keep waiting here indefinitely. So let us say that thread with lower ID came, and since it was willing to enter into the critical section, and other thread with greater thread ID was also willing to enter into the critical section. Both of them are willing, but since the thread having lower thread ID will make this condition as false, it will enter into the critical section. And yeah, and it might happen that it finishes critical section. Meanwhile, please note that the thread with greater thread ID was looping here. It might finish, thread with lower thread ID might finish critical section, do unlock, and again enter the critical section. uh, and that might and this thing might happen indefinitely, and thread with higher thread ID might keep on looping here, and yeah, this might keep on happening because whenever the thread which was the thread with lower ID will enter the critical section and will come out and will again enter, because this condition will always be false for it, and in that way it will never get a chance to enter the critical section. In that way starvation can happen, or progress is not guaranteed, is what I'll say. Is there any question? We use k less than k that can execute multiple times. We only work if k is completely done. Can execute multiple times. We only works after k is completely done, which could be a long time. Yeah, in that sense, yeah, that is also correct that progress is not. Yeah, in that way, it's correct that the thread which is having higher thread ID might keep on waiting here indefinitely. So yeah, it might keep on waiting indefinitely here, and in that sense progress is not guaranteed. And one more question, is mutual exclusion guaranteed is the question. Let us say that we have just this condition k less than me here instead of this entire thing. Then is mutual exclusion guaranteed or not? Can you please think about it, or give some example where it is guaranteed or it is not guaranteed? Any suggestions? Okay, anyways, I'll there was some there is some noise from someone's end. Can you please mute? Otherwise okay, in case you have any questions, you can unmute and ask, but otherwise please mute yourself so that conversation can go smoothly. There is some suggestion, yes, because each ID is unique. Order is first thread ID and then next and so on. Okay, I guess probably we are missing something here. Probably I might be also wrong, but let us see this thing. According to me, mutual exclusion is also not guaranteed. Let us understand why. Let us say this, please note that this label checking or checking that label of k comma, sorry, not label of k, but k is less than me is inside this loop. So there exists k less than me and this k less than me here is inside a loop. So let us say that thread, let's say some thread 4, thread with ID 4 came and it wanted to enter the critical section, and it was checking if there is some thread whose ID is less than my ID. So let's say at that time there were no threads. So it checked for thread 0. Is that thread 0 who is willing to enter the critical section? It is having ID less than my ID. So at that time thread 0 was not there. So it moved on. It checked for thread 1, thread 2. And meanwhile, what happened? Okay, so it checked for thread 1, thread 2, thread 3, but no one was there. So yeah, fine. So no one is there. So thread 4 entered the critical section. But now let's say what happened, thread 0 came. Meanwhile, thread 4 was in the critical section. It saw that okay, there is some flag 4 which has willingness to enter into the critical section, but my ID, which is k equals to my ID, which is me, which is 0, is not greater than the ID of the thread which is having ID equals to 4. So k is 4 for the thread 0. So 4 is not less than 0. So it will also enter the critical section. So I hope you are getting it. So let's say some higher ID thread came and at that time no thread was present, then it will enter the critical section. And also later if lower ID thread comes, then it will also enter the critical section if we just have this k less than me. So I hope that you are getting it, that mutual exclusion is also not guaranteed if we just use this thing. If we just use k less than me, then mutual exclusion is also not guaranteed, as well as progress is also not guaranteed. I hope you are getting the reason for both of them.
So I had a question. So is the flag still
Yeah.
in the checking of the flag is still there in the condition, right? That's the assumption. Only the statement label of k comma k less than label of me comma me is being replaced with k less than me. Is that right?
Yes, this statement, this thing is already there. It is not changed. What is there after this logical end? This thing is being replaced by k less than. Yes.
Understood.
Yeah. Please go ahead.
Yeah. So essentially, the flag, the willingness is, it's possible for the later thread ID to go ahead with the execution because it sees that the flag is true.
No, it will see that flag is false for other
False.
threads.
Exactly.
False
Yeah.
for other threads.
Yeah.
because no other thread was there at that time. So it will go inside, and later some lower thread ID thread came. It saw that some other thread has willingness, but my ID is less than that thread, so it will
So
also
it will
enter.
also go ahead.
For that, this will become false. So I hope you are getting this. And because of this, if we use this thing, then mutual exclusion is also not guaranteed, as well as progress. So I hope that is clear. So that was the second part. So again, first part was this. If we use this, then mutual exclusion is not guaranteed. If we use this, then mutual exclusion as well as progress is not guaranteed. The second thing. And now comes the third question. My third question is also simple. Let's say we use this. Okay, let us not type here because it is simple. Uh, let us say that I replace this less than by greater than. Just that change I make here. Instead of less than, I make greater than. Then what will happen? Rest all things remains the same. Just I replace this less than by greater than. Then what can happen? Is there mutual exclusion guaranteed? Is there progress? Or first of all, let us just talk about mutual exclusion. If it is not guaranteed, then let us not move further. Is mutual exclusion guaranteed? Please think about it. We go back to teaching. So Gokul has some questions. Sir, what about this? Okay, I missed this question. What, while unlock shouldn't it be reset label? Okay, I guess probably we missed here, but yeah, for unlock, it's not reset level, it must be reset flag, because label is ever increasing. If you see, label will keep on increasing. It's an ever increasing kind of token. So please think of it like that, that at shop, that token number keeps on increasing, right? You don't need to reset it unless it's some overflow or some kind of case. But yeah, label is ever increasing. We are just saying, for unlock, we are just saying that, okay, the thread that, the current thread that executed critical section is now no longer willing to enter into the critical section since it has already finished the critical section. So I hope that is clear. We just don't need to reset the label, because whenever next time that thread will enter, it will get the label as the maximum value which is there inside this label array plus 1. So that is not an issue. It will always get the higher and higher value unless there is an overflow. So that part I am just ignoring, but yeah, uh, other than that, it will always get higher value than what is present in that this label array maximum value. uh, there are some responses. No progress, mutual exclusion, yes. Okay. Okay, just let us talk about mutual exclusion first. Yeah, only the first thread in the stack will enter. Okay, it might go negative. Yes, overflow can happen, that I told, but just for this, just for this example, let us assume that there is this overflow issue doesn't exist. In that case, resetting label is not needed, is what I am suggesting. Yeah, but we need to take care of that overflow, which is correct. Yeah, it's a correct observation that we need to take care of overflow issue. Okay, let us try to understand this thing also. So let us see if mutual exclusion is guaranteed if I replace this less than by greater than symbol. So when mutual exclusion is not guaranteed, when more than two or more than two threads enters the critical section. So if I replace this less than by greater than, can it happen that more than two threads will enter into the critical section? So yeah, let us understand this with an example. So let us say that initially no thread was there inside the critical section, and thread 0 came. And since thread 0, I mean, there is no other thread, it will make its willingness to true by setting flag equals to true. It will get label as 1, because 1 plus max label, which I mean labels are initially 0, so it will get 1 plus 0, which is 1. It will see that no other flag is willing, so this itself will be false, and it will enter into the critical section. So thread 0 has entered the critical section. Now let's say a few other threads came. Thread 2, 3, 4. I mean, thread with ID 2, 3, 4 came. For them, they'll get label accordingly. So thread with ID 1, sorry, thread with ID 1, 2, 3 came. Sorry, not 2, 3, 4. Thread with ID 1, 2, 3 came. Thread with ID 0 is already there inside the critical section. Thread with ID 1, 2, and 3 came. They'll make flag to true. They'll get the label as 2, 3, 4, because 1 was the max label at that time. And since they execute, even they can get the same label, right? So if they execute this statement at the same time, then they might also get the same label. So in that case, they might get the label as 1 plus max, which is 2. But let us say that they execute this instruction one after the another, then they might get the label value as 2, 3, and 4. And so thread with ID 1 got label as 2, thread with ID 2 got label as 3, and thread with ID 3 got label as 4. Now, since there are multiple threads who want to enter into the critical section, so for them this is true. And for the thread with ID 4, with ID 3, this condition will also be true, because this is now greater than. So label of k, which is this is false, because label of k, which is 0 for the which is 1 for the thread with ID 0, 1 is greater than 4 is false, right? So I hope you are getting it. For thread with ID 0, which was already there in critical section, label is 1. And for thread with ID 3, which is willing to enter into the critical section, label is 4. So 1 is greater than 4, because this is now greater than. 1 is greater than 4 is false. And since this is false, this while loop will not keep on looping infinitely, and it will also enter into the critical section. So thread with 0 and 4, thread with ID 0 and 3 are now into the critical section, and hence mutual exclusion is not guaranteed if we replace this less than by greater than. I hope that is clear. If you have any questions for that, this replacement by greater one, that scenario one, then please unmute yourself and ask. Okay. Anyways, if there are no questions, then yeah. So please note that mutual exclusion is not guaranteed. And let's say if you want to ensure mutual exclusion while replacing this less than by greater than, then we need to ensure that label is initialized to int max instead of 0. And instead of max here, we need to replace it by min. And then we can put this greater than instead of less than. So with this, I am hoping that there are no questions. So, okay. Sorry, so I am hoping that you got this point, and we understood the different scenarios also, like replacements for this conditions. And yeah, I think this should help you people to understand this bakery's algorithm better. But with this, let's move on. So yeah, one thing that you should observe is that this max is not atomic. So as I said earlier, it might happen that multiple threads find the max value inside this label array simultaneously, and they get the same value as the max value, and they replace it by 1 plus that value. So it might happen that since max is not atomic, multiple threads can get the same label value. Yeah, so I hope that point is clear, that max is not atomic, and hence multiple threads can get the same same label value here. And the second point to note here is that this code will only work in the absence of caches, and in presence of caches, caches mutual exclusion is not guaranteed, because the reason is the same as we understood in the previous lecture, that this boolean flag of size n and this int label of size n both should be volatile, should be declared as volatile. Otherwise, it might happen that whatever value is written inside this flag and label array might be cached locally for each. I mean, each of the cores by each of the caches of the cores, L1 caches basically, and it might not be written into the main memory. And other thread might read the stale value which is there in main memory, and hence it might cause issues, or it might lead to I mean, it might cause that mutual exclusion is not guaranteed because of that. So I hope that is clear. So this both this flag as well as label should be declared as volatile. And yeah, so this issue should be kept in mind. And with this, let's move on to the next slide. Okay, any questions up till this point? So there are no questions. That's fine. So let us understand if this bakery algorithm will work on GPU or not. So yeah, I mean, when we talk about GPU, we think about warps, right? So across the warps, this algorithm is same as CPU, because across the warp, the execution is asynchronous, right? Two threads which are in different warp can execute in any manner, and I mean in any fashion, and that is how the two threads of CPU execute. But what happens for the warp threads? Uh, if let's say this lock code, this code for locking, I mean this function for locking the, I mean this function which performs the locking part is executed by the warp threads, then what will happen? Is there any catastrophic event that can happen if warp threads execute this lock code? Can anyone please, I mean, request you to think about it, and if anyone have any thoughts about it, then please feel free to express those thoughts. So question is, I mean, I'm reiterating the question again, that this lock method is executed by the this warp thread. So 32 threads which forms a single warp are executing this lock function. And please note that warp threads execute in SIMD fashion. So they'll execute this statement, then once this is finished by all the warp threads, they'll move on to this statement and so on, and then this while condition. So is there any issue or potential issue that can happen by this SIMD sort of execution? Okay, there is some suggestion. Gokul is saying that there will be a deadlock. Most threads will be stuck in while loop. They'll wait for one thread to complete, but that thread will wait for rest of the work. Perfect. So that was what I was expecting. So let us understand what will happen. So let us say that warp threads are executing this while sorry, not while, but this lock function. So they'll execute this statement, then this statement, then this statement. So for all the warp threads, flag will be set to true. So all are willing to enter into the critical section. For all of them, initially label was 0. So for all of them, label will be 1 plus max label, which is 1 plus 0, which is 1. For all of them, label is 1. They all are willing to enter into the critical section. So for them, flag is true. Now comes this part. So what will happen here? This is true, right? Because multiple threads are willing to enter into the critical section. And let's come to this condition. So label of k less than k, label of k comma k less than label of me comma b, comma me. So this condition will be true only for one thread. And which thread will be that? That will be thread 0, right? Because for all of them, label is same, but the lowest thread ID among the warp thread is 0, assuming that warp has threads from 0 to 31, which is, sorry, IDs from 0 to 31. So in that case, this condition will be only true for one of the warp thread, and that warp thread that warp thread wants to move further. But since we know that warp executes in SIMD fashion, and since all other threads are stuck here, because this condition is also true and this is also true, all other 31 threads of warps are stuck here, and only one thread wants to move further, but it can't move because of that SIMD sort of execution. So it will also keep on indefinitely waiting for these threads which are looping here. And this is exactly the scenario of deadlock, right? That one thread one thread wants to move, but it can't move because other threads are waiting here. And yeah, that is due to SIMD execution. I hope you are getting this, that we'll be facing deadlock here if we execute this lock function with one warp or 32 warp. I mean 32 threads of a single warp. Okay, any questions up till this point? If there are no, then we'll move further. Okay, assuming that there are no questions, let's move further. So, yeah, on GPUs, let us understand this thing. So, on GPUs, lock are typically prohibited because, I mean, if you see, we generally use locks on the CPU, right? I mean, but if you people might have studied this in operating systems, we use locks for handling the critical section for multiple threads and so on. But on GPUs, that is prohibited. I mean, we can use it, but it's prohibited because there is large cost involved with it. Because on CPUs, threads are CPU has few tens of threads, while GPUs have hundreds of thousands of threads. So, due to such large number of threads and due to massive multi-threading, the cost or the overhead involved with the locks is high. So you can think like this, that let's say you have just one book and there are 10 people who wants to read that book. So that 10, if there are less people or 10 people or 5 people, then only that 5 people need to coordinate with each other to read that book. But let's say you have an entire institute, or let's say all the students of the institute want to read that single book. In that case, there will be a chaos, right? Because there is one single book and there are thousands of students who want to read that single book. So due to this, there can be chaos, and there will be, I mean, there will be a lot of scheduling that will be involved. And yeah, typically there can be multiple issues with it also. So that is exactly what is the scenario with locks on the GPU. In GPU, we have just that one variable, and we are trying to we have that just one variable or one critical section that one thread just can, I mean, that only one thread can execute at one time, and we have thousands of threads who want to enter into that critical section, and this thing can lead to a problem. So typically locks are prohibited on GPUs, but there are different ways in which we can deal with this locking problem on GPUs, which we'll study. So lock are prohibited, but they are feasible. So if you want to use, you can use it. But yeah, this bakery algorithm we need to modify a bit because it will lead to deadlock for warp threads. And lock are feasible, and they are implemented using something called as atomics on the GPU. And let us see what is atomic now. So let us start with a new subtopic in this synchronization, which is atomic. Any questions up till this point? Okay, I guess there are no questions. This for the okay. Anyways, there are no questions, so let us move further. So let us try to understand what the atomics are, and then we'll move further. So atomics are sort of a primitive operation. So primitive operation meaning the basic operations like add, subtract, and all those things. So those primitive operations like add and subtract and all those things, multiplication, are supported by the hardware. In that way, this atomics are also primitive operations whose whose effects are visible either fully or none. So it won't happen that so consider it like a black box. So you can only see its state before the execution and after the execution. So if, let's say, if you are having a variable and if you want to add something to that variable atomically, then either you will see its value before addition or after addition, but you won't see its value during the addition. So that is what is the atomicity. So you won't see the intermediate state, but you will see the initial or final state. So that is what is atomic is. So let us take one analogy here. So let us say that you might have seen that subway sort of thing, right? So train, let's say there is a train which is passing from a subway or some tunnel. So when train enters into that tunnel, I mean, before the train enters into that tunnel, you might be able to see passengers, what they are doing and sort of things. If you are a viewer who is not sitting in the train and you are standing somewhere outside, and there is some train who is entering into the tunnel, then you might be able to see what the passengers are doing inside the train before it enters the tunnel. But when it enters the tunnel, you want to be able to see what's happening with the train, because you are an outside viewer. And similarly, so that portion is like a black box, right? That tunnel is like a black box. You won't be able to see what is happening while the train is going through the tunnel. And once the train comes out of the tunnel, you will be again able to see what's the status of the train and so on. So that tunnel portion is like a black box, and that is what atomic does. You will be able to see the initial state and the final state, but you want to be able to see the intermediate state. And for doing this thing, you need some hardware support. You won't be able to do it at the as a programmer. So this atomically testing and setting and all those things need some hardware support. And yeah, that is one thing. And the second thing is that there are several variants for the atomic instruction. So one is atomic guess, another is atomic min, and then there is atomic add, and there are many more supported on CUDA. So this all statements are this all instructions are supported on CUDA. So atomic guess is atomic uh, yeah, so it is compare and swap. Atomic CAS meaning compare and swap. So it compares the value and swaps if some condition is met. Similarly, atomic min is used for finding the minimum across two values in the CUDA. So we'll see examples for this, and also this atomic add. So it atomically adds the value inside a particular variable. So we'll see examples related to all of this three instructions. But yeah. So yeah, again, next thing to note here is that this atomics are applicable both for the global memory and the shared memory. So if you people might remember, then there was that sync thread, which was only applicable for the threads of the thread block, and hence we can only use for the threads of the thread block. But this atomics are, I mean, they're across all the threads of the correct, or all the threads of the GPU. So they are I mean, that they are visible across. I mean, whatever we'll do for this, I mean, do using this instructions, they'll be visible across all the threads. So it's applicable for both shared and global memory. So yeah, that is the point that I want to make. And with this, let's get started with our first sort of classwork. Yeah, but before that, is there any question also? Okay, there are few questions. Sir, these atomic instructions are to be used only inside the kernel. Yes. So this let me. Yeah. So this atomic guess, atomic min, atomic add, all these are used inside the kernel code, and these are specifically for the CUDA. So there, I think this can only be supported inside the. I mean, you can only use this inside the kernel. For CPUs, there might be something else that you want to use, but for CPUs also atomics are supported. But yeah, these three things, this atomic guess, atomic mean, and atomic add, are for the GPUs. Okay. Whether atomics can be applied to memory transfer. Okay, I'm not sure about this, if atomics can be applied to memory transfer, but I haven't seen any example so far which does the a memory transfer atomically. Okay, I'll say that I'm not sure about this thing, but there might be something using which you might be able to do memory transfer atomically, but I need to check this. Okay, so I haven't seen any function or some API doing this thing, so I need to check this one. Okay. Okay, so let us get back to our discussion. So let us start with our first classwork of atomics. So let us say that we have this code. There is some initialization happening for this variable. We have CUDA malloc, CUDA malloc the value of x. Let us assume that, and then we are launching the kernel with two threads, 2,1. So these two threads are from different thread blocks. Please note that 2,1 means two separate thread blocks, and then we are we are passing the address of x to the kernel, which is stored in int star x, and then the value of this what I can say, yeah, this memory location which is pointed by x, which is given, which is, I mean, which can be received using x, this square brace 0 is being incremented by using this plus plus operator. So I hope you are getting this, that we are allocating the memory of for this. I mean, we are allocating some memory using CUDA malloc, and then we are passing pointer to that memory, which is stored. I mean, address to that memory, which is stored in this variable x to the GPU kernel, which is stored inside this again variable, inside this pointer variable x, and then what we are doing is we are incrementing the value which is stored in that allocated memory on the GPU using the using this plus plus uh, using this plus plus thing. And yeah, so my question is, what are the possible values for the x after this kernel finishes its execution? So request you people to think about it. Yeah, so we are incrementing x with plus plus operator, and I want you people to think about what are the possible values for the x after this kernel finishes its execution. Okay, Gokul has suggested something. Maybe like in SQL, using commit, you could try to implement that perhaps. Okay, thanks for that suggestion. Uh, yeah, okay. Gokul is saying 1, 2, or 0. No CUDA device synchronize. Okay, let us assume that CUDA device synchronize is also there. But assuming that there is CUDA device synchronize, what can be the value? Is the question. Please think about it. I'll wait here for a few seconds so that you people can try.
As they are from different blocks, so they will run in asynchronous mode. So
Yes.
any value it can take 0, 1, 2.
Okay. How can it take the value 0?
No, not 0, 1 or 2.
Oh, okay. Let us see this. But let me see if others have tried it or not. Okay. Gokul is saying 1 or 2. Varun is also saying 1 or 2. 2 means first increment, then next increment. Okay. Okay, I think you people are getting it correctly. There is something else. 1 means both heads same. Okay. Yeah, I think your thinking or the intuition behind it is correct. But yeah, let us understand it step by step. So again, I also have mentioned this thing before, that this single statement, this x plus equals to 0, sorry, plus plus x, then square bracket 0, end of this square bracket, is split into this three assembly level instructions. And yeah, please note that this whenever we write this plus plus x, it's just a syntactic sugar for this thing, right? Uh, it's equivalent to this. And as we have already studied that, right, this thing is splitted into 3 assembly level instructions. Yeah, which is this 3 assembly level instruction, in which we are first loading the value of loading the value which is present in x of 0 into some register r1. Then we are incrementing this register incrementing the value which is present inside this register, and then we are storing the value of this register in the x0, which is the memory location from where we have loaded the value. Okay, so what are the possible execution orders that can occur out of this? I mean, when two threads try to execute this 3 assembly level statement in any fashion, so there can be multiple possible ways. But if we try to determine what can be the value of x, then it can be 2, and those two values can occur if those can occur when we have this first we have this this execution pattern that loading is happening simultaneously, then they both are also incrementing independently. So please note that loading is happening simultaneously, but only one load will happen at one time, because this read and write instruction are just a single instruction at the assembly level, and they are done atomically for each thread. So either thread 1 will load, then thread 2, or thread 2 will load and then thread 1. Either of them can happen. But since they are happening one after another, they'll see the same initial value, which is 0. Then they'll increment the value of R1 and R2, which is the value register in which the value is loaded, simultaneously, because since they have different registers, they can do this simultaneously. So they both will increment value to 1 and 1 respectively, and then both of them will try to write into that memory location x of 0, and based this store can happen in any order. First the thread 2 can store, and then thread 1, and then or it can happen vice versa, thread 1 will store and then thread 2. But in either of case, since the value which is present inside the register is 1, if any, in any of the case, if any, in any of the interleaving, the value which is final value which is stored in x of 0 is 1, right? So okay, I hope that is clear. So if this is the execution pattern, then the final value will be 1. But if they execute one after the another, let's say this entire thing happens for the thread 1, and then once this store is finished, and then this thread 2 starts executing its load and increment and then store, then in that case the value which is stored in x0 will be 1 after the store for the thread 1, by the thread 1, and then when the thread 2 loads the value from x0 into R2, it will be 1, and then it will increment and then it will store. So in that case the answer will be 2. So I hope that you are getting that two answers are possible, which is 1 and 2. Yeah, assuming that this thing is true, assuming that they are either the threads from two different thread block or from two different warp. So I hope that is clear. But let us yeah, so first of all, final value stored in x0 could be 1, or it can be 1 or 2. But let us do another class work. What will happen if the kernel configuration is 1, 2, meaning that they are the threads from the same warp. So again, this entire thing is same, kernel is same, but just this one thing is changed. Here it is 1 and here it is 2 now. So instead of launching two kernel with two different threads of different thread block, we want to launch the kernel with just two threads of same warp. Then what can be the output? What can be the different values of x that can occur after the execution of this kernel is finished? Please think about it and post your answers into the chat. Okay, Gokul is saying 1. Okay. Okay, would you like to explain why it is 1, Gokul? Okay, Varun is also saying 1. Okay. Okay, anyways, I think that yeah, I think that you are getting it. So yeah, when we launch kernel using this configuration, instead of instead of getting output as 1 or 2, the output can be either 1 or 2 for this configuration, right? This one. But when we launch the kernel as this using this configuration, the output or the final value stored in x0 will always be 1. Actually, this statement, this statement is for this this launch configuration. So when we launch the kernel using this launch configuration, the final value stored in x0 is always 1. Actually, it could be 1 only rather than 2. So let us understand why the value can only be 1 rather than 2. And for understanding that, let us see how the warp threads execute. So as we know that warp threads execute in SIMD fashion, so they'll first execute this load statement. So both of them will load at the same time. Since load are atomic, I mean just a single assembly level instruction, so they'll be interleaved in any manner. So thread 0 and thread 1 of the warp will execute this load and this load and this load in any order, arbitrary order. So both of them will have value loaded into that register as 0. Then both of them will increment the value of register in SIMD fashion. So both of them will be at this instruction. And once that is finished, both of them will again try to store. And since store is again one assembly level, just one instruction at assembly level, the value that will be stored in x0 can also be in any order. So thread 0 can do store first or then thread 1 or in either order. But in any of the case, uh, I mean in either of the case, the value which is stored in x0, x of 0 will be always 1, right? Because the way in which we execute is SIMD, right? Single instruction, multiple data. So only this load will happen, and then only this warp threads will move to increment, and then only this warp thread will move to store. So if you see, if this order is followed by the warp thread, then final value that x will store is always 1, right? So yeah, if we launch using this configuration, then output could be 1 rather than 2. Is what is the observation that you should, you people should not should make a note of it. And yeah, small homework that I would like you people to try out is that if if let's say x0 is also splitted in multiple instruction, because if you see this x of 0, x of 0, this thing x of 0 is actually expanded to this thing, right? Because it's a pointer dereferencing, so it's x plus this x is base address plus this 0 is offset. And then once we move base address, we move our pointer from base address plus some offset, we try to dereference using this star operator, right? So it is just a syntactic sugar for this thing. This x of 0 is syntactic sugar for this thing. And if okay, so the question is that if x of 0 is also splitted into multiple instruction, then what are the possible output of this output out of this kernel D kernel? What will be the possible values of possible values that can be stored in X? And the second question or second homework that I want to give is, let's say we have just 2 threads here, right? Or yeah, let's say we have just 2 threads. If we launch the kernel with multiple threads, not just 2 threads, then what can be the output that is stored? What can be the value of X is the question. So please try this question out. It will help you in understanding how the warp threads. Not warp threads, but how the multiple threads work, and what can be the different execution patterns, and it will help you in understanding all those things. And it will be good exercise for you people. So please try that out as part of your homework.
So I have a question. So storing is not really a SIMD. Storing on a common variable for multiple threads within the same warp is not a SIMD operation. It can occur in any way.
Yeah,
Right?
actually it is because of the way the uh, the short answer is that it's not SIMD because it has to be interleaved in some fashion, because storing into that particular memory location even by 2 different threads can't happen at the same time. That is because the way the memory work, only one write can happen to that particular memory location, even if there are 100 threads or 1000 threads who want to write into that location at a particular moment. So I hope that is clear. Yeah,
And
but yeah.
one other
Yeah.
question is, so in split into multiple instructions means I didn't get it. You have written star x plus 0. So
Yeah.
uh, how is that multiple instructions? Then what will be the
Oh,
next instruction?
okay, so again, so star x plus equals to 0. If you want to implement, if you look this thing as an assembly level instruction, It might be split into multiple steps, right, at the assembly level. So for example, you might load the address of X in some register. Then you might add something into that ADDR, right? Some offset, let's say offset you want to add. Then you might want to store it, right? Once you are done with it. So you'll again store that index, and then you'll dereference it, right? Because for getting its value, you also again need to dereference it. So this can be the multiple steps that might occur at the assembly level. So let's assume that this val is for dereferencing, and so these are the multiple steps that might happen while dereferencing this, or like for this x equals to 0, so not x equals to 0 but x of 0, this part. I hope you are getting this point.
Yes, thanks.
Okay, so I mean the key takeaway is that this is not a single assembly level instruction. The way we are splitting this thing, this x or okay, go back here. The way we are splitting this thing, this x plus plus or this x equals to x plus 1 statement into 3 assembly level statement, in the same manner this thing or this thing can be split into multiple assembly level statements like this. So yeah, so I hope that is clear. So if that split is happening, then what can be the possible values that can be stored in the x? Yeah, so that please try as a homework so that you can learn how the different execution patterns can occur and all those things. Okay, so with this, let's move on to the next slide. So this is one small use case or a small scenario where atomics are being kind of I mean, or a real world application of the atomics. So let us try to understand this. Let us say that you have I mean, you have this ATM. I mean, this what I can say that there are this ATM. Uh, I mean ATM machines, right, from which you can withdraw some money. So there are these two ATM machines, and then there are two twin brothers or two twin sisters who are going to this ATM machines for withdrawing some rupee at the same time. So both of them go to that ATM machine. Both of them tries to withdraw the cash from that ATM machine at the same time from both of that ATM machine. And let us assume that they have the joint account from which they are withdrawing the money from the ATM machine, and that joint account just have 1,000 rupees, and they are trying to withdraw that 1,000 rupees at the same time from two different ATM machines. And and in order to do that, what this system will do, right? So what this ATM machine will do, it will check if the balance is greater than 1,000, which is greater than or equal to 1,000, which is the case because they have the joint account and the balance is 1,000, right? So it's greater than or equal to 1,000. So this check is done. So yeah, this check is done, and since both of them are doing it simultaneously, this will pass for both of them. Then what then this system will do, or ATM machine will do, it will reduce, which is, I mean, since this is correct, they'll reduce the balance by 1,000 and will give cash to the user. So it might happen that if these two steps are not done atomically, these two steps, checking of the balance and reducing the balance and giving the cash to the user, if these two steps are not done atomically, then it might happen that twin brothers or twin sisters who go to this ATM machine might get 200 rupees. But if you observe, the balance was only 1,000, right? That balance of that joint account was just 1,000. So this is not okay, right? So the key point here to observe is that yeah. So first of all, the execution pattern is this that we saw, right? That loading is happening simultaneously. Then here decrement is happening, not increment, because we are reducing the balance, and then storing is happening. So final result that will be stored, I mean, or the final balance that will occur will be 0, right? Because 1000 is deducted and then it is stored, but both value of R1 and R2 will be 0, because initial balance was 1000, and the value that is deducted from both the ATM systems is 1000. So 1000 minus 1000 is 0, and both will try to store 0. So the final value that is, I mean, or the final balance that will occur is 0. But what ended up happening is that they received 2000 rupees and the initial balance was just 1000. So in order to implement this algorithm, or this ATM system, what I would say is that algorithm in this ATM system properly, which is checking the balance and then reducing the balance, and then if the balance is uh, proper, or if it is meeting this condition, and then we reduce the balance and give cash to the user, otherwise we issue error. So in order to implement this algorithm properly, what we need to take care is these two statements, which is checking of the balance and reduction of the balance by that particular amount should be done atomically. If that is done, if checking of the balance and reduction of the balance is done atomically, then this scenario will not happen, that two twin brothers or sister might end up getting 200 rupees. So that is what is done in the ATMs, or I mean in normal banking systems, where this checking and the reduction is done atomically. And this is some real world example of how, I mean, the real world example where the atomics are being used. So yeah, I hope that this is clear. If there are any questions here, then you people can ask. Okay, any questions up till this point? Okay, if there are no questions, then we'll move to the next slide. Okay, so in order to okay, so we saw that there is this issue with this code, right? That there is data is occurring here, that any interleaving is possible, and hence the value can be either 1 or 2. And in order to ensure this all or none behavior, which is actually ensured by atomics, what we can do is we can replace this thing, this this statement, by atomic increment. And what this thing ensures is that testing of this variable, I mean, or testing of the value inside this variable and incrementing it by 1, incrementing it by 1 will happen atomically. So if you see this entire thing, loading and then storing, loading, incrementing and storing, this entire thing will happen atomically. And when this is happening, no other threads can do loading or incrementing and storing. So if we replace this thing by this atomic increment, which is having this syntax, in which we first argument is the address of the variable, and the second argument is some upper bound, which says that if value becomes this value becomes a value of this variable x becomes equals to this upper bound, then you just wrap around. I mean, wrap around meaning replace the value of x by 0. So first is the address, or the yeah, this it's actually the address of the variable that we want to atomically increment, and second is that wrap around the limit. So I hope that syntax is clear, and the way it works is as I explained. This testing, incrementing, and setting is done atomically by atomic increment. And yeah, so the key point here to observe is that if you launch the kernel with k1 comma, I mean, as using this configuration, which is k1 comma k2, and it should ensure that, I mean, using this atomic increment should ensure that the final value that you will get after execution of this kernel, assuming that you have launched using this configuration, the final value of the variable, I mean, final value stored in this memory location, which is pointed by variable x, will be k1 into k2, irrespective of whatever is the execution order of the threads. So yeah, I hope that this is clear. If there are any questions, then quickly please post them on the chat. Any questions up till this point? Okay, so we have seen this atomic increment briefly here, but probably we'll also revisit this in the later slides if we get time. And yeah, next comes the atomic gas, but I don't want to start the atomic gas because since we have very less time left with us, just 3 minutes. So probably I'll push this atomic gas to the next lecture. And yeah, so in next lecture we'll see the atomic gas. Then we'll also see how to implement lock using atomic gas and how to implement single, which is something which we'll see in the next lecture. And then we'll start with the barrier in the next lecture. So probably for the 2 days lecture we'll end here because I don't want to start with a new instruction, atomic instruction today because it might take some time. So yeah, so I'll stop here. If you have any questions, I'll be here for a couple of more minutes, and yeah, probably then we'll disperse if you don't have any questions further. There is some questions, sir. Would atomic cause divergence? Yeah, in some sense, yes, it will cause divergence. But in fact, if you see atomics, how they are implemented is there is a queue system maintained. So let us say that even let us say that warp threads or across the warps, if the threads want to perform some operation atomically, then they'll be pushed into the queue. And based on the way, I mean, based on the order they are pushed into the queue, they'll be executed. So yeah, for warp threads, it might lead to some divergence. So that is correct observation, I would say. But in more sense, atomics will lead to something called as serial executions. Serial execution, which I'll say, I mean, warp or thread divergence won't be a proper term for it. Yeah, I hope that is clear. In some sense, you can say that for warp thread, it is some sort of divergence because in divergence also threads execute. I mean, warp threads execute in that stalled manner. But yeah, here the reason for the divergence is different. Here the reason is that we want one thread to execute at one time, even if it's a warp thread. So it's some sort of that divergence only, but I won't tell it as, I mean, I won't say it as a thread divergence. I hope that is clear. If you feel that something was missing, then you can unmute yourself and ask. Any questions apart from this on today's content or anything else from the previous lectures or anything?
Sir, in case of CPU,
Okay.
so we have hardware implementation of the semaphores. So test
Yes.
and set instructions are added. So can we consider these atomics and all other these mechanisms in GPU is equivalent to that in CPU?
Yes. If you talk from the functionality point of view, then the functionality that atomics provide on the CPU is similar to the functionality that this atomic gas and all this atomic increment, atomic add provides on the GPU. So functionality wise, both of them are same, but implementation wise, they might differ. And I am not very much aware about the implementation details from the, I mean, from the very hardware perspective. So I want to be able to comment upon this implementation aspects. But yeah, functionality wise, both are same. Okay. Any further questions?
Sir, in this case, in the last example you have shown, So that you have already explained in response of one question, I think from Mr. Gokul, that when whatever be the order of the execution of the threads, so ultimately the result will be K1 into K2. That means it is equivalent to execution of the serial execution of the threads.
Yes, in some
So,
sense you can say that. Yeah. Yeah.
so
Please go
in
ahead.
that case, so sir, if it is true, then it is equivalent to the concept of serialization in RDBMS. So that so whether obviously there will be some sort of that is performance degradation, whether in the name of divergence or not, whatever be.
Yes, yeah, so I think you are correct here. So there will be definitely a performance penalty that will go because of this atomics. And yeah, so as I told in the previous lecture, so atomics and all this synchronization constructs are the one which will incur you the highest penalty. Then, sorry about this. Then is something, then there is some this memory things, right? So memory has the second highest penalty. Then comes the computation aspect. So yeah, you are correct that this serialization happens here. If you see properly, uh, when we replace it with atomic, the serialization happens here, and each and every thread of the GPU, I mean, each and every thread with which we launch the kernel will serially execute this increment, right? I mean, it will increment one by one. It won't happen that multiple threads can increment at the same time after we do this atomic. So serialization happens and there is a performance penalty, and it's actually very high compared to any memory access or any computation aspect. So this is a crucial issue from the GPU programming, CUDA programming point of view, and we need to see how to deal with this issue. In general, we need to take care such that, we need to write our code such that there are as minimum synchronization construct as possible, like such atomics and all those things. So I hope that this is clear.
Yes, sir.
Can
Yes,
you
sir. Thank you, sir.
there are any further
Thank you, sir.
questions?